Guys, this is Hannah back at it again for our last lab of the semester, Lab 5, Faraday's Law. So in this lab, the purpose was to watch a magnet falling through a tube of aluminum foil, and we took 5 trials to record the time it takes for the magnet to get through the tube each time. We used aluminum foil because it's a non-ferrous metal, which means that the magnet won't stick to the tube, and that's very important because that would mess up our lab completely. The next thing that we did was we modeled the interaction computationally, and then we compared our observed data with the data that we got from the computational model. So I used the Biot-Savart law, Faraday's law, the superposition principle, Newton's second law, or the momentum position update principle, and Newton's third law for this lab. Lots of stuff, but I'll explain it later. And then my results were that my average observed time was 0.48 seconds, and the time for the computational model for the magnet to go through the tube was 3.548 seconds. I think some of the possible causes for this discrepancy could be the experimental error in the magnetic moment, which would be from lab 3, and also the low density of the aluminum ring because it wasn't compact together. So here is a table of my data from the dropping the magnet in the tube, as you saw in the picture earlier. The average time it took was 0.48 seconds, and falling in free space took about half the time, and we'll find out why later. So after we observed the magnet going through the tube in real life, we wanted to simulate that in GlowScript using the equations that we've learned and the principles that we've learned previously. So we started by creating our magnet using the magnetic moment from lab 3, which I had to be 2.2558. So here we're starting with all the functions that we'll use repeatedly in a loop. And first is the Biot-Savart law, and this is the general equation that we used in lab 3 to calculate a magnetic field. And then we can use that to calculate the magnetic flux, since we know it's just the integral of the magnetic field with some stuff that we already know, the n hat times dA, just the change in the area. So after we figure out the flux, we know that the magnitude of the flux is the same as the EMF, so that will be helpful to us in the future. So here we have a loop using the functions from the last slide to calculate the force from the bar on the aluminum tube, and conversely through Newton's third law, the force on the bar from the tube. So we can calculate the induced current using the formula I equals EMF over R in step 4, which we can plug into the formula F equals I times delta L cross B. Since we know that delta L is perpendicular to the magnetic field from the magnet, we know that the magnitude of the magnetic force is just going to be I delta L B times sine theta, where sine theta is the angle between the force and the y-axis. Finally, we can use this updated force with the momentum update principle, Newton's second law, to find the time that it takes for the magnet to go through the tube. So here's a picture of the magnet as it's going through the tube before the simulation is over. And I wanted to explain this because it's kind of cool to me. So using the right-hand rule, we find that when the magnet's above each individual loop, the induced current will be clockwise, represented in blue. But when it's underneath the loop, it would be pointing in the opposite direction, since the magnetic field is pointing up. So going through the tube, you're going to have induced currents going in opposite directions, depending on where the magnet is at in relation to each separate ring that we're calculating the current at. So here's the graph that I got for the velocity versus time, and it's very interesting. So basically, you can see that it's increasing in the negative direction since it's going down. The velocity is increasing in the negative direction until it gets to a certain point where it starts slowing down, and that's when it's entering the tube. And then it quickly reaches about a constant speed, and then speeds up once again once it leaves the tube. And that makes sense because the sum of the induced currents is constant. We have an equal and opposite force, so it's going to be a constant speed when you're going through the tube. So the time that I got for my simulation was 3.548 seconds, which is pretty different from my experimental value of 0.48 seconds. And I explained this a little earlier, but I'm thinking that the possible causes were experimental error in the magnetic moment, something that I would have done in lab 3, or just the fact that the aluminum ring has a lower density than expected because the aluminum wasn't very packed, so that could have been a problem as well. So if the resistivity of the conductor was reduced as close as possible to 0, that would mean that the induced current would be higher, so we'd have a higher force on the magnet, so that the magnet would then move slower. And then if the holes or slots were cut into the tube, those rings with an open loop would have 0 current, so the magnet would be moving faster at those points. So overall, the time for the magnet to go through that tube would be faster.